Hi, and welcome back to Quantum Programming with Cirq. I'm Abe.
And I'm Catherine.
Let's get started with quantum programming.
The goal of quantum programming is to manipulate the quantum states of your qubits in such a way that the solution to your problem of interest can be obtained. The first step in programming a quantum computer is creating a quantum circuit. Once we've picked a specific problem and identified how a quantum computer may be able to solve it, we need to build a circuit which describes a series of operations that act on the qubits in your quantum computer. You've probably already seen images of quantum circuits while reading quantum computing papers or online.
So now let's imagine you have indeed identified a quantum circuit that can be used to solve a problem. How would you build it in Cirq? And how would you test that circuit on your laptop before running it on a real quantum computer? This episode will answer that first question about building the circuit, and then the next set of episodes will answer the second question about seeing how it performs on your laptop. And we will do all of this work using Cirq. And Cirq is an open source quantum computing programming framework. You can get more information about Cirq by going to our website at quantumai.google. Cirq allows us to build the quantum circuits that we are interested in using Python.
Great, let's get started.
As always, we'll get started by opening up Colab. In episode 1, we welcomed you to this video series and showed you that we'll be writing all of our code in Colab. Just as a reminder, you can open Colab by going to colab.research.google.com and logging in with your Google account. Once you're here, you can quickly install Cirq by writing the command pip install Cirq. And you can put this exclamation mark at the beginning to say that this is a command. And once this is done, we can see that Cirq has properly installed by importing it and saying import Cirq. So Catherine, what is our goal for today?
Our goal today is to build this quantum circuit you're seeing here in the Colab in Cirq. It comes from page 54 of the first edition of my favorite introductory quantum computing textbook, which is Mermin's Quantum Computer Science, an Introduction.
And we'll do this in a few different ways just to demonstrate how powerful Cirq is, and then you can pick whichever method works best for you as you do your work. Okay, so when we see this circuit, the first thing to think about is the structure of the circuit itself. We see that there are 6 qubits, so we'll start by creating 6 qubits in Cirq. I can do this by typing myQubit0 is cirq.lineQubit0. Now, since Python starts indexing things at 0, I've called these things myQubit0 and started numbering it at 0. And we'll do this one by one for other qubits as well. So I'll say myQubit1 is cirq.lineQubit1. And moving on, I'll say myQubit6 is cirq.lineQubit6. This has now created a line of 6 qubits, and I'm ready to use them in a quantum circuit. And in fact, I can convince myself that this is indeed the set of qubits by printing any one of them and seeing its number being printed out.
Perhaps it will be a little tedious to define the qubits one by one if we need a lot of qubits. Shall we try a shortcut?
That's right, sure. So there's also another way that you can do this. So for something like this, where you're wanting to quickly create a line of many qubits, in this case 6 of them, I can say cirq.lineQubit.range and pass on a number, in this case 6. And you see that that creates a list of 6 of those qubits. And you can prove this to yourself by printing out myQubits. And you see there's now line qubit 0, 1, all the way up to 5. And so there are 6 of them here. Before I start working with these qubits, I want to show you a couple of other ways to create qubits. So what I'm going to do here is start by telling you about grid qubits. So sometimes you might be interested in defining your quantum circuit to act not just on a line of qubits, but on a grid of them. And this becomes particularly relevant when you begin working with quantum hardware.
Let me show you an example here of a physical qubit grid. Here in the Colab, we have a photo of our Sycamore quantum processor and an image of a layout of qubits on the processor. When you're working with hardware, you will be defining operations that operate on a qubit grid just like this.
Right, and to do this in Cirq, you can say Cirq cirq.gridQubit and identify the coordinates where you want that qubit to be created. So in this case, I'll say 0, 1 and call that my qubit 0. And unlike in the previous case where the qubit was identified with one number when we did line qubits, here I need to specify two numbers corresponding to where that qubit is located in the grid on an XY plane. This becomes especially useful when you want to create grids with some sort of shape. So for example, a rectangle or a square. For example, here, I'm just going to say cirq.gridQubit.rectangle and say I want 3 rows and 2 columns. And I can print this out by saying print my qubits. And you see that I indeed have a grid of qubits where Cirq has created 3 points along the x-axis, so those are the first numbers, and 2 points along the y-axis, and those are the number of columns that we asked for. Similarly, I can do something like this to create a square. I can say cirq.gridQubit.square and pass on the size of that square. And you can see now I have a grid of qubits that is exactly shaped like a square with 3 numbers on x and y. I want to show you one last method for creating qubits. And I'm going to go back to the textbook that Catherine mentioned earlier and flip to page 76, where I find this picture of a quantum circuit. And each of the qubits in this picture are named something that helps us identify them. So you can see they're called x0, x1, x2, and x3.
Right.
Catherine, do you see this in the textbook?
Yep.
So this naming of the qubits is also possible in Cirq. And I can do that by saying cirq.namedQubit and pass on the name that I want for that particular qubit. So if I want to create 3 qubits, just like in the picture, I can say cirq.nameQubit x1, cirq.nameQubit x2, and cirq.nameQubit x3. And you see if I print them now, they're identified by their name instead of their location, just like we saw for line qubits and grid qubits.
Okay, let's quickly recap what we've learned so far about creating qubits. So there's 3 ways of creating qubits. We can create them by naming them one by one, we can create a line of qubits, or we can create a grid of qubits.
And now it's time to build our quantum circuit. Remember, we started this whole episode by wanting to build a quantum circuit in the image here. We will not get into the details of how each of these operations on the qubits work, and we'll instead focus on how to build the circuit itself using these operations.
So looking at the circuit, we need to start by applying a Hadamard gate to every qubit.
Right, so what I'll do again is create a line of 6 qubits because we need 6 of them. And then I'm going to create an empty circuit by saying cirq.circuit. And then I'm going to append H gates to that circuit by saying cirq.h, pass in each of the qubits, and then append that to the circuit. And I'll do this 6 times just to make sure that I have each of the Hadamard gates here. And just to make sure everything is going as I'm planning, I'll print out that circuit, and you can see that indeed we have a line of 6 qubits with H gates applied to each of them.
To speed this up, we can actually create a loop instead of applying the gate on each qubit one by one.
You're right. And actually, I can do this by saying cirq.h qubit for qubit in my qubits, and then enclose that in a list and create a circuit out of that list. And I'll call that my circuit. And you see, if I print my circuit, it reproduces exactly what we had before. In fact, because this is such a common thing to do when you're building your circuit, Cirq offers you another way to make this even simpler by writing cirq.h.onEach and then pass on just a list of your qubits. And so I'll say cirq.h.onEach my qubits and create a circuit out of just that list and print it out. And you see it reproduces exactly what we had before.
Effectively, Cirq creates the loop for you when you use onEach and pass it a list of qubits.
Exactly. All right, so now if we look closely at the image again for the quantum circuit, we see that all of the qubits are initialized in the state 0, except the last one, which is initialized in the state 1. In Cirq, qubits are initialized in the state 0 by default, so we don't need to do anything to the top 5 qubits, except for that last qubit where we need to flip it from 0 to 1. Now you might remember that we can do this in quantum computing by applying an X gate. And so we'll apply that gate before the series of H gates to initialize all of the qubits. And I can do that by saying Cirq.X on that last qubit. And then I'll create a circuit with just that operation. And then to that circuit, I will append the Hadamard gate. So I'll say Cirq.H qubit for qubit in my qubits. And I'll do one new thing that you haven't seen here before, which is to say the strategy by which I want to insert those Hadamard gates is Cirq.InsertStrategy.earliest. And you see, if I print the circuit, now we have a series of Hadamard gates on all of the qubits and an X gate on that last one before a Hadamard is applied to it.
So all the Hadamard gates have been placed as far to the left as possible here. Shall we explain why this happened?
Sure. So this is actually Cirq's default insertion strategy when you add new operations onto qubits. And by doing this, Cirq is saying that at the very moment at the beginning, while the X gate is being applied to that last qubit, I can bring in those H gates on all the other qubits. And then once that moment passes, we can apply an H gate on that last qubit. Actually, this is a point where I want to ask a question to the audience. I'd like to ask, just tell us in the comments down below why you think this is a good default strategy and why it might be useful. And just to give you a hint about how to think through this, I'll just say think about realistic considerations when you're running these quantum circuits on real quantum processors.
I think I know the answer, but of course I will not give it away. And I look forward to seeing all of your comments. Hold on though, what if we do not want to use this default insertion strategy? Abe, can you show us how to make sure the X gate sits in the first moment and all the Hadamard gates go into the next moment?
You got it. We can do this explicitly in Cirq by saying we want to define a moment. So I'll say Cirq.moment. This is a new thing we haven't done before. And I'll say within that first moment, let's do an X gate on that last qubit. And then in a second moment, I'll apply a Hadamard gate on all of the qubits. And I'll call these two moment 0 and moment 1 and append to an empty circuit these two moments one by one. And now when I print the circuit, you see that we have the X gate applied first and then the chain of Hadamard gates applied second. But let's pause here for a moment. This concept of moments is quite important in Cirq, and I'll actually take you to the documentation page just to show you this very useful picture. If we click on our website, quantumai.google, and hover over to the tab for our software and go to Cirq's documentation, you'll see that there are many places where you could go. In particular, I'll take you to the place where you build circuits and point out this very useful picture. And at the end of the day, what this picture is trying to tell you is that quantum circuits are collections of moments, and each of these moments contains operations on qubits themselves.
Okay, so let's summarize what we've done so far. First of all, we've learned a few different methods for defining the qubits that we will be working with. We've also learned that we can perform operations on these qubits by using Cirq's gates. And we've learned how to specify in which moment in the circuit every operation should be performed.
That's right. And I like to say this by summarizing that circuits are collections of moments, and these moments themselves are made up of operations. And the operations themselves are made up of gates acting on qubits. All right, now that we've learned all of this, let's make that quantum circuit and test it quickly. So I'll go and start over from scratch and create, again, a series of qubits. I'll need 6 of them. So I'll say my circuit is Cirq.circuit, and my qubits are Cirq.lineQubit.range, 6 of them. I will explicitly reset all of the qubits to the 0 state by saying Cirq.reset, and I'll say reset qubit for qubit in my qubits and create a loop. And I'll create a moment for that set of resets, and I'll append that moment into the circuit. Then I'll flip that last qubit to 1 from its initial state of 0 by applying an X gate. And I will append that to the circuit. And then I'll apply the Hadamard gates to the circuit by saying I want to do Cirq.hqubit for qubit in my qubit. And I'll create a moment out of these and append it to the circuit. And then if we go back to the figure, we can see that there are a series of C0 gates that we need to put into our circuit. They go from qubits 0 to 5, 1 to 5, and 4 to 5. So I'll say Cirq.C0, my qubits 0 to my qubits 5, my qubits 1 to my qubits 5, and my qubits 4 to my qubits 5. And finally, I'll bring in those H gates again, and we can print out the circuit to see what we've done. Now you see we've created exactly the figure that we wanted to build in this quantum circuit, and we have that chain of resets at the beginning, that X gate that flips the last qubit from 0 to 1, the chain of Hadamards, controlled NOT gates, and again, the chain of Hadamard gates.
Great, let's now test our circuit.
Sure. Before we move on, I just want to quickly mention that this quantum circuit describes an instance of the Bernstein-Vazirani algorithm with a specific case of a bit string that you can read off from that chain of C0 gates. In this particular case, we're thinking about the case 1, 1, 0, 0, and 1. If you don't know about this algorithm, that's fine. We'll put a link in the description for you to read more about it. I just wanted to quickly mention that for those who know what this circuit is doing. Now I'll do one more thing and quickly show you how to simulate the behavior of this quantum circuit, and we'll simulate its behavior on a perfect quantum computer, and we can mimic that perfect quantum computer on our laptop. To do this, since we have a very small circuit, we can run a simulation very quickly in Cirq, and I'll need to do two things. First, I'll insert measurements at the end of the quantum circuit. So I'll say Cirq.measure qubit for qubit in my qubits, and then pass on a number of qubits that describe all of them. And then I'll create a moment out of these and call that measurement gates, and I'll append that to our circuit. And then I'll say, Cirq, give me your default simulator, and I'll call that sim. And I'll run my circuit on sim and print out the result. If I print the result, what I see here is qubit 0 is in the state 1, qubit 1 is in the state 1, qubit 2 is in the state 0, and so on. And that chain of results shows you 1, 1, 0, 0, 1, which corresponds exactly to that pattern of C0 gates that I mentioned before.
I hope this video has given you a helpful overview of how you can define your quantum circuits in Cirq. There are many ways, of course, to build circuits, but the core idea is to define operations on your qubits and to place those operations into a set of moments that together form a quantum circuit. In upcoming episodes, we will show you various techniques for simulating quantum circuits on your laptop. That looks good.
Oh, wait, hold on.
Wake up, dude.
Access this, God.
No cursing.
Bonus time, let's do something fun, Catherine. So for those of you who have had extensive experience with Python, you can bring the full power of Python to building these quantum circuits. Let's take the same circuit that we've been building so far, but take as much advantage of Python to create it in the least number of lines. So I'll start by defining that pattern of controlled NOT gates, or CX gates, by saying CX pattern is 11001, and I'll build off of this. So how many qubits do I need to describe that pattern? Of course, I need n, which is the length of that CX pattern, and I'll need as many qubits as there are n plus 1 for that one last qubit. So I'll create a list of qubits, the ones that will have the controlled X originating from, and I'll call them my qubits X for X in range n, so that's all of the qubits, if the pattern says that it has a 1 there. And I'll create a target qubit list, which is simply that last qubit, and I'll start building my circuit line by line. I'll create an empty array here and start saying Cirq.reset each of my qubits, and I'll put star here to expand that list of qubits. I'll say apply that X gate to that last qubit. I will apply a moment here where I do the Hadamard gates on each of the qubits. And then I will apply a C0 on each of the qubits. And the way I'm going to do this is by saying C0 dot on each, and then I'll create a zip that matches the source qubits for the CX. So that's zip between CX qubits, and the target qubits, which is exactly that last qubit over and over again. So I'll multiply that target qubit by as many as there are CX qubits. And then I'll create another moment where I apply the Hadamard gates again, and then measure all of the qubits and close this off. Let's print the circuit. And you see this is exactly the same circuit that we built before. And just like we did before, I'll say Cirq.simulator is my simulator. And I'll run this circuit on the simulator and print out the result. Voila, we see the pattern 11001. We'll see you in the next episode. Bye.
See you in the next episode. Bye!